Okay, so last time we stopped here, we actually talked about the reflection and refraction. So yeah, so I suppose you should have learned this in high school physics about the optic part. So here, I think also this one, the total internal reflection, you should have already learned. So the idea here is if the source of light is emitted from the material that has a higher index of refraction, so when it goes to the surface, okay, when it goes to the boundary, then if this incident angle is large enough, then yeah, all the light will be reflected. Okay. Otherwise, if this incident angle is not large enough, let's say for this one A, B, C, or D, okay, if this angle is not large enough, then part of the light will go through, and then part of it will be reflected. It depends on the angle. It doesn't really mean that okay, half of it go through, half of it reflect. It actually depends on the angle. So I will not talk about this detail here, but anyway, so you can simply understand it as part of it go through, part of it reflects. But okay, as you know, if this part we have a larger index of refraction, which means that the refraction angle should be larger than the infraction angle. And up to this part, okay, so here, when this incident angle is equal to theta c, the refracted angle turns out to be 90 degree. Because from the Snell's law, we have an n1 sine of theta 1 equals n2 sine of theta 2. Here we assume that n1 is larger than n2, and then here if we consider sine of theta 2 to be n1 over n2 and then sine of theta 1, okay, which means that this n1 over n2 is larger than 1. N1 over N2 is larger than 1 because N1 is larger than N2, N1 over N2 is larger than 1. So for some of the, for one of the angles, so we might have, which means that if sine of theta c equals N2 over N1, because N2 over N1 is smaller than 1, okay, smaller than 1, then theta c will have a solution, so that if sine of theta c equals to n2 over n1, in that case substitute to here, then it turns the right hand side turns out to be 1, okay, which means that theta 2 will be 90 degree. But if theta in is larger than theta c, so in that case right hand side will be larger than 1, so there won't be any real solution for theta 2. Okay, so that's the problem here. So we don't have a solution for the refractive angle, which means that all the light will be reflected. Okay, so like F and G will be here. All the light is reflected. This thing is called the total internal reflection. So I suppose you should also have learned this phenomenon in high school optics. Okay, but this part will be a little bit more advanced. Okay, of course we don't go into the details. Of course, this one is somehow related to the quantum physics. Okay, related to the quantum physics. So I just let you know this phenomenon. Okay, of course it is out of the It's not in the textbook. I just find it on the internet. Okay, so of course, if you're interested, you can check the link here. It has more description. But the idea here is, if we have two beams, okay, with 45, 90 degrees, so This is 90 degree, 90 degree, 45, 45, 45, 45. So right angle, triangle. Okay, so the idea here is if these two streams is placed separately. Okay, of course these two are supposed to be glasses, so which has the end which is larger than 1. Okay, so here we assume this is the air. This is air outside. So and then this is glass. Okay, this is glass. This is also glass. Okay, so the glass has a larger index of refraction. Okay, so here. And we suppose that, okay, so this one 45 degree is already larger than this one we call the critical angle. Critical angle. So we all already suppose that, okay, this theta I, okay, theta I is already larger than theta C. Okay, suppose like this. So if these two are placing far enough, so you can ignore the bottom, the top right one, so that all the light will be total internal reflected, okay, on this surface. Okay, so this is the first case, easy to understood, okay, just as the previous page. And then for the second case, if we place these two, okay, sorry, maybe go to this one first. If we place these two, okay, touching each other, the two faces touching each other, so we suppose that these two surfaces are flat enough so that there won't be any gaps in between. Okay, so they are perfectly flat and then no gaps in between. So in that case, it will be like they are single square stream. Okay, so in that case, if the light enters from the left side, okay, go to this one, it won't see a boundary here, okay, because two of them are touching each other perfectly, so there won't be any gap, and then it just go through, so there won't be any reflection. So it is also easy to understand, okay, it is also easy to understand. But the thing is that we have something called the frustrated total internal reflection, FTIR. Okay, so in the middle is called the FTIR. OK， 就是 frustrated in Chinese is 沮丧的，但我不知道整个，本来这个叫全反射，那我不确定是不是叫沮丧的全反射，还是有一个什么中文的名字。So anyway, so for this FTIR, the idea here is we just leave a very thin gap, okay, very thin gap. Oh, how thin? I'm not really sure. It depends. But the idea here is we try to leave air film, okay? Leave the air film is made to be thin out by progressively squeezing the film together harder until they make intimate contact. Okay, 就是他们刚好没接触到，但是有一个很窄的缝在中间。Okay, so in that case, there are some interesting property here. So it will be like if it is far away enough, okay, total internal reflection. If they are touching each other, all the stuff will go through. But here, if it is there's a gap in between, you'll see, okay. So there may be, yeah, actually, part of the light will be able to go through. And then part of the light will be, okay, so this part is total internal reflection. And then this is no reflection, okay? So part of it will go through, we'll be able to go through. It's just like there's some probability that a proton may be able to go through to jump through a gap. Okay, so this is very interesting. In quantum physics, it is also a joke, okay? It's like, okay, yeah, of course, as a human being, we may not be able to go through a wall. But for a particle, yeah, if there's a potential wall, okay, so suppose there's a potential wall. This is the potential. If a particle, okay, let's say a particle is here, okay, so yeah, if it has kinetic energy smaller than this potential energy, okay, smaller than UO, okay, so in in the sense of classical mechanics, this particle or this ball may not be able to go through this potential wall. But in quantum mechanics, if this wall is thin enough, this particle may be able to go through with a certain probability between 0 and 1. So this is this interesting phenomenon. 就是如果有一个缝的话，它就会有一个几率穿过这个缝隙，就是好像这个它其实也是一个量子的效应。就是量子效应的话，就是它有一个经典的一个笑话，就是说人没有办法穿过一个墙，但是一个粒子的话，如果有一个 potential wall 的话，它是有几率穿过去的，而且可以算出来的。以前教这个第38章的时候有推导那个几率。So actually, this is so-called the total internal reflection. Just let you know. And then here is the table of the refraction indices. So for the vacuum, the index is defined to be 1, okay, because n, okay, so we calling n is actually the c over the v, okay, so v is the speed of light in that material, and then this is the speed of light in vacuum. So for the vacuum itself, it's c over c itself, so it's exactly 1. Okay, but for the air, it is really close to 1, slightly larger than 1.00029. So usually if it is air, okay, we pretend, okay, or maybe we just approximately okay, think that it is really close to, okay, really close to vacuum for the electromagnetic characteristic. Yeah, because we have something like the mu 0, we have epsilon naught, mu naught. Okay, and for other material, they have different epsilon and mu. Okay, for air, okay, these two constant in the air is really close to epsilon naught and mu naught. So the speed of light, okay, c is of course 1 over mu naught epsilon naught, and then for v is actually 1 over mu epsilon. Okay, so if they are very close to mu naught epsilon naught, okay, so v is very close to c. But if if it is a magnetic material, mu might be much larger than mu 0, or if it is dielectric, then this A will be much larger than epsilon naught. Okay, so, and then for the water, okay, 1.33 for our 4 over 3, and then for some other stuff, and okay, here the diamond, okay, the diamond has a much greater indices as 2.42. Okay, so that's why ladies like the diamond, because it can actually reflect. Okay, it can actually reflect the light, so that okay, the diamond looks very charming. So yeah. Okay, so actually for this part is actually the last part in chapter 33. It's about the polarization of by refraction. Okay, so polarization by refraction. We can also okay, make some light with to be polarized rather than using a filter. Okay, in the previous slide, in the last lecture, we have already mentioned that if we have some polarized light, and then if we have some filter, okay, polarizing filter, Then after the unpolarized light goes through, the intensity will drop by half, and then the light become polarized light. Okay, depends on the direction of the polarizing filter. And if it is polarized light go through the filter, it depends on the angle between the polarizing direction and the filter direction. Okay, it need to multiply the original I0 by cosine of theta squared. Here is another way. Okay, if we don't have the polarizing filter, we may have another method to have some polarized light. Okay, so here we suppose the incident light is also unpolarized. Okay, incident unpolarized rate from the top left. Okay, going to the boundary here. Okay, this is the boundary. So the top part is air, the bottom part is glass. Okay, it can be other material. Yeah, just an example. So here it says a ray of unpolarized light in air is incident on a glass surface at the Brewster angle. So this one we call it the Brewster angle, theta b. Okay, so what happened when it is theta in? Okay, theta 1 is equal to theta b. Okay, so the idea here is that it says if the incident angle is equal to the Brewster angle, actually here, okay, so what will happen? It will happen to be like, of course, the refracted angle will be actually the same as the incident angle. Okay, so this will be theta b, okay, so nothing special here. The refracted angle is, of course, also follow the Snell's law, okay? N1 sine of theta 1 equals N2 sine of theta 2. Yeah, but here, what the interesting thing is, the reflected wave, okay, only the reflected wave will be polarized. Okay, only the reflected wave will be polarized. But the refracted wave will be partially polarized. Okay, which means that all the so you can consider if it is unpolarized light, okay, if it is unpolarized light, this direction is the propagation direction of the EM wave. Okay, so the E field must be perpendicular to this direction. So maybe, okay, part of it is like this, okay. Part of it is inside outside the page, okay. This part is actually perpendicular to it, okay. So, perpendicular to the surface, or actually on the surface. So in that case, all the component that is parallel to the plane will go through. Okay, all the green part go through. But for the orange part of it refracted, part of it go through. So that this part is called this part will be the polarized light, and then this part will be partially polarized. Okay, so so it's said to be, okay, the reflected light consists only of component perpendicular to the page, and is thus polarized, okay, perpendicular to the page. And then the reflected light is like a weaker component perpendicular, okay, so-called partially polarized. And then of course we don't try to derive, okay, why it would be like that. It is to be more too advanced. Okay, just let you know the conclusion is that theta b will be arctangent of n2 over n1, also related to the trigonometry function, trig function. Okay, so here, okay, here of course n2 is larger than n1, okay, arctangent of n2 over n1 would be larger than 45 degrees in this case. Okay, so so here we have an interesting property that is theta b plus theta r to be 90 degrees. Okay, so here we have this one is theta b, this one is theta b, this one is theta r. Okay, so of course, if you're familiar with geometry. Okay, this one and this one add up to be 90 degree, and this one is 180 degree. So of course this one is 90 degree. Okay, this one is 90 degree. So in some sense, we don't actually need to know. We don't actually need to know n1 and what n1 n2 is, and then calculate the Brewster angle. The idea here is like, of course, we may be able to observe the incident angle, reflected angle, or refracted angle. The idea here is we just need to adjust the incident angle such that this ray and this ray are perpendicular to each other. Then it will be the Brewster angle. It will be the Brewster angle, and then this part will be polarized. Okay, because just like this page. Okay, so we may be able to. Okay, so here's the source, so that okay the light is incident from top left. Okay, to the surface. This will be the refracted. This one will be the reflected ray. Okay, so we may be able to observe the angle easily. Okay, so of course we can just simply verify that why this characteristic will be true. So the idea here is, okay, what we know is that okay, the first one is of course the Snell's law. N1 sine of theta 1 is equal to N2 sine of theta 2, and then also theta 1 is equal to theta b, which is arctangent of N2 over N1. Okay, let me see how to derive. Okay, so theta b, we can actually draw out a right angle triangle. This is N2, this is N1, and this is theta b. Okay, so this one will be N1 square plus N2 square, and then take the square root of the whole thing. Yeah, so here we will be okay, so here theta 1 is actually theta b. Okay, so here we need to calculate sine of theta 1. So we may be able to write out the form of sine of theta 1 or sine of theta b, yeah, because we have already drawn out this right angle triangle. So here sine of theta 2 will be actually N1 over N2 sine of theta 1. Okay, and according to that right angle triangle, sine of theta 1 will be N2 over square root of N1 square plus N2 square. Okay, so in this case, we may be able to cancel this N2 with this N2. Okay, so in that case, this is nothing but N1 over square root of N1 square plus N2 square. So by observing this one, okay, so N1 over this square root stuff will be like a cosine of theta b. Okay, so sine of theta 2 is cosine of theta b. So using some trick identity, it is actually sine of 90 degree minus theta b. Okay, so which means that this one theta 2 is actually 90 degree minus theta b. Or maybe we can just write as a theta out referring to the refracted. So in that case, theta 2 plus theta b is actually 90 degree. So we have this one. Okay, theta b plus theta out. Okay, actually that one is theta out will be 90 degree in that particular case. Okay, so this is the other method to generate some polarized light without the polarizing filter. So here we have some additional example. So let's take a look at it. So this one is it says unpolarized light is sent into a system of 3 polarizing sheet. Okay, so here we have a 1, 2, and 3. Okay, the angle theta 1, theta 2, and theta 3 of the polarizing direction are measured counterclockwise. Okay, counterclockwise from the positive direction of y-axis. Okay, so this is the positive y-axis, They are not shown to scale. They are not shown to scale. Just let you know, okay, we have some angle. Okay, don't try to measure it, measure this angle and then try to answer. Okay, so the angle theta 1, theta 3 are fixed, but theta 2 can be varied. Okay, the intensity of the light emerging from the sheet 3 as a function of theta 2. Okay, so theta 2. So the intensity, okay, after going through the last one. Okay, so this is I, and then it refers to the intensity at the output. Okay, of course, at the very beginning, it will be like I0, something like that. Okay, yeah, so what is the percentage of the what is the percentage of the light in initial intensity is transmitted by the system when theta 2 is 30 degree? It's 30 degree. Of course, it is already drawn in this figure. It's already drawn in this figure like here. But of course, we don't know, okay, how large it is. So we should be able to find it out. Okay, so we should be able to observe a bit. Okay, so of course we can easily see that, okay, this one is 0, this one is also 0, this one is also 0. Okay, so here the idea here is we observe that I is equal to 0 at theta 2 equals 0 degree, 90 degree, and 180 degree. Okay, something like that. Okay, so which means that theta 2, okay, the sheet number 2 should be perpendicular to the first one and the third one during this angle. Okay, and of course this one, okay, so 0 degree, 100 degree can be considered to be the same. Okay, so pointing to this direction and that direction is considered to be the same. So so we can simply imagine that one of the sheet number 1 and sheet number 3 will be aligned to 0 degree, and the other one will be aligned to 90 degree. So in that case, we will say without loss of generality. Okay, 就是中文叫做不失一般性。Okay, so we assume theta 1 to be 0 degree, theta 3 to be 90 degree. Yeah, because one of it will be 0 degree and the other one will be 90 degree. So we can assume that theta 1 to be 0 degree, theta 3 will be 90 degree. And then what I mentioned without loss of generality means you will be able to assume theta 1 to be 90 degree, theta 3 to be 0 degree. It will give you the same thing. It will give you the same thing. Okay, so why not just choosing one? Okay, so yeah, because they are just symmetry. Okay, so in that case we will be able to, okay, so after going through this observation, okay, so we have this 0 point at this 3 angle, we may be able to inference that, okay, so this yeah, one of it aligned to 0 degree and the other one aligned to 90 degree. Then, okay, it just go through, okay, so this is 0 degree, this is 30 degree, theta 2 is 30 degree, this is 90 degree. So it'll be able to, easy to calculate. So IF over I will be, the first one is, at the very beginning is unpolarized light, right? Yes, at the very beginning is unpolarized light. Okay, so after going through the first one, this is the 1/2, okay, the 1/2 density, okay, from unpolarized light to polarized light, the density dropped by half. And then from Yeah, so this is 1/2, okay? This is 1/2. And then the other part is 0 degree, 30 degrees, so we need to multiply by cosine 30 degrees square. So here we have a cosine of 30 degrees square. This is the second one. And then for the third one, from 30 degree to 90 degree, so we have another cosine of 60 degrees square. So it turns out to be 9.4%, okay, by pressing the calculator. So this is pretty much about it. So this is slightly twist from this one, okay, but based on some inference, it turns out to be the same as this one, okay. It turns out to be, of course, this is 0 degree, 60 degree, 90 degree, but yeah, they are quite similar, so they turn out to have the same answer, okay. Turns out to have the same answer. Okay, so and then the second one is even a little bit more interesting, okay. Of course, when I was a year 1 student, I'm not easy to understand this stuff, okay. So because it is like an application to the calculus, a simple application to the derivative, okay, the derivative. Okay, so here, let's see what it says. So here it says a certain helium-neon laser, okay, 氦氖 laser emits red light in a narrow band of wavelengths, okay, narrow band of wavelengths. So which means that if we try to do some statistics about the wavelength of this laser, well, red light laser, okay, so it turns out to be something like this. This will be something like a normal distribution. Okay. Yes, it is supposed to be ideally with a single frequency. Yeah, because it tries to oscillate in some structure so that only a single frequency may be able to survive. The other will be like canceling each other. But it is, yeah, practically there will be a very narrow bandwidth. This narrow bandwidth, we call it the delta lambda. Okay, the delta lambda. Okay, so here it says that this very narrow band of wavelength center. Okay, so this is the center. We may call it lambda 0. Okay, lambda 0 is actually this value, 632.8 nanometer, and with a wavelength width. Okay, the wavelength width is 0.01 nanometer. Okay, so this is the width. Okay, how to define? We have the peak. Okay, the peak intensity. Okay, the peak density, and then we make it half. Okay, so this is the peak. Okay, this is half. This is half of the peak intensity. Okay, and then we try to measure this. Measure the width, okay, measure the width, and then this is called the band, okay, the bandwidth, okay, the bandwidth of this wavelength. Okay, so it asks you what is the corresponding frequency width for the emission. Yeah, of course we know that as an EM wave, it should satisfy C equals F lambda. C equals F lambda. So that, okay, so this is like a histogram. So everything is like, okay, so for this one, we have a bar like this, we have a bar like that. And of course, for every single sample, we may be able to use this C equals F lambda to calculate the corresponding frequency. Okay, so that in that case, we are also able to draw it with an axis of frequency. With a frequency, it turns out to be like, we have a F0, and then we also have have a normal distribution, okay, normal distribution like this, and then it also have a peak, and then it also have a half bandwidth, okay. So this is the delta f. So for every single one, okay, we will be able to plug it in here, and then we may be able to draw something like this. Okay, so I just ask you what is the width here. What is the width here? Okay, so actually we can do it two ways. Okay, of course in the textbook it just show you how we can use the derivative, okay, to simplify the calculation. So it is like df equals d, okay, c over lambda. Yeah, because here we can write it as f equals c over lambda. Okay, we can consider, okay, c is a constant, so f is a function of lambda. Okay, they are depending on each other. They are dependent on. You cannot just change f without changing lambda. Okay, if f is larger, lambda will be shorter. Okay, and vice versa. So f will be a function of lambda. So here we can write it as a df equals dcd lambda, or if it is more like a derivative, you can consider it to be df d lambda equals d lambda and then c over lambda. Okay, it will be even more easy to understand. Yeah, but simply speaking, okay, so this one should be lambda. So this one is d lambda. Okay, so write out this d lambda. Okay, but here we just skip this d lambda here, so they should be supposed to be the same thing. Okay, so taking the derivative here will be like c over, this is lambda to lambda inverse. Okay, so the derivative will be negative lambda square and then d lambda, okay, according to the chain rule. Okay, so this part is according to the chain rule. This is the derivative of this function. Okay, so everything makes sense. So if we would like to take the absolute value, okay, absolute value of df, okay, we write it as delta f, and if you like, you can also consider to be a df or delta f df. They usually refer to similar stuff. Okay, so here we just ignore this negative sign, so we have a c over lambda square and then d lambda. So we can here actually plug in all the values. C will be 3 times 10 to the 8th power, and then lambda is actually this one, or lambda 0, okay, or lambda 0. So or lambda 0 here. Okay, lambda 0 here. So actually is 632.8. Nano is 10 to negative 9 and then whole square. And then d lambda is this one, 0.0100 times 10 to negative 9. Okay, okay, like this. Okay, so actually you can just press the calculator. You can see that this is actually 7.49 gigahertz. Okay, gigahertz. Okay, so 7.49 gigahertz. Okay, so we may consider this bandwidth is quite width, but yeah, for the visible light, okay, it is not that width. It is not that width, yeah, because the visible light has a much higher frequency than the RF. Okay, if it is RF, it is a very large bandwidth, or even for millimeter wave, it is a very large bandwidth. Yeah, the other way to consider is that actually you can actually consider the other way. It's like this one and this point. Okay, you can consider this one to be lambda 1 and then this point to be lambda 2. So you may be able to find that, okay, lambda 1 will be this lambda 0 minus delta lambda over 2. And then lambda 2 will be lambda 0 plus delta lambda over 2. And then you plug in these two to this equation. You will be able to find F1 to be C over lambda 1 and then F2 to be C over lambda 2. It turns out to be that this will be F1, this will be F2, yeah, because they are inversely proportional. So that if lambda 1 is smaller than the middle point, and then F1 will be larger than the middle point. Lambda 2 is larger than the middle point, F2 will go into the left side. Okay, so of course you can also consider delta F by F1 minus F2. Turns out to be this. Of course, the value here won't be exactly the same. There may be some numerical error, yeah, because this is also a some approximation, okay, approximation for the derivative. It just assumes that the slope, okay, the slope will be constant for a nano bandwidth. Yeah, but actually for this one you can consider to be somewhat precise. Yeah, but yeah, usually that is not that important unless you are doing some very precise experiment. Yeah, but anyway, this is an additional example to get you familiar with how to apply the derivative, okay, to approximate something. Okay, so that, yeah, probably this one is considered to be easy to calculate rather than, okay, going through this one, or maybe, okay, if you are not that familiar with the derivative, okay, maybe you feel the red part is easier to understand. Okay, so